This lecture is a description of the analysis of the data obtained in the one-dimensional, perfectly inelastic collision laboratory experiment. For those of you enrolled in Conceptual Physics AB, you will complete the laboratory exercise on the handouts as a mini-lab. For those of you enrolled in Physics AB, Honors Physics AB, and AP Physics C, you will analyze the data and write up a formal laboratory report. Okay, let me go ahead and take you through the laboratory exercise. Okay, so in this lab, we're taking a look at a one-dimensional, perfectly inelastic collision. Recall, of course, in a perfectly inelastic collision that the carts stick together after the collision. I'll be colliding air track carts together, and I will have them stick together by means of Velcro, for example, like so. So I'm going to refer to the red cart as M1, and I'm going to refer to the gold cart as M2. Okay, now the purpose, first of all, of the experiment is to simply verify that momentum is conserved during the collision. Okay, now there is a little bit of theory behind the experiment. Those of you that will be writing up a laboratory report for the experiment, you must include this theory in the first section of your lab report. Okay, so we're going to use our air track like so. I'm going to assume that the air track is horizontal and frictionless. Okay, and then we have right here the red cart, which we're going to refer to as M1. And then I'll give it a push down the track and let go of it, such that it then continues at a constant velocity. That constant velocity is going to be referred to as V1 naught. Okay, and then we have the gold cart here. This guy we're going to refer to as M2. The gold cart is initially at rest, so V2 naught is equal to 0. Let's go ahead and total up the initial momentum of the system. That is the total amount of mass times velocity. We're going to refer to this as P initial. So the total amount of momentum of the system prior to the collision is simply M1 times V1 naught. Okay, and then the carts will collide and stick together. After they do stick together, they then move down the track at a constant final velocity, which is common to both. We're going to refer to that as V final. So here's what the situation looks like after the collision. So here's our air track like so. Here's M1 and M2 stuck together by means of the Velcro. They then move down the track together with a final velocity here. We'll just refer to as V final. So now let's go ahead and total up the final momentum of the system after the collision. That is the total amount of MV. We'll call this P final. So P final is going to equal M1 plus M2 times V final. And in theory, the initial momentum should equal the final momentum. So basically what we're going to do is we're going to measure out everything and show that in fact the two momenta, initial and final, are the same value. Okay, so here's then what we obtained. Here's our procedure. Okay, so here's my air track like so. As you'll see me do, I attach then to M1 a piece of strip tape like this that's threaded through the spark timer, which is held back here. Here's M2 over here, initially at rest. And then in sequence, I do the following. I turn on the air, turn on the timer, and then I push M1 and let go of it, such that after I let go of it, it moves down the track at a constant velocity, V1 naught. Okay, at this point, go ahead and pause this video and then take a look at the other video that I've posted for you that shows me obtaining data for the experiment. So go ahead and take a look at that video now. Okay, now that you've seen that video, when I examined the strip tape that I obtained, it is a good tape for us to use. Okay, here's basically what the tape will look like. You'll see this in a series of photographs that are also posted in the folder. Okay, now I'm going to draw here the portion of the tape that's important. The portion of the tape that basically describes the following. after I let go of M1 and it moves down the track at a constant velocity V1 naught, and then the collision occurs, and then the two objects stuck together move down the track at a constant velocity V final. So if we examine this crucial portion of the tape, it will then look like the following. First of all, while the red cart is moving down the track at a constant velocity V1 naught, because the velocity is constant, you'll see the dots evenly spaced, like so. And then the collision happens. The collision happens, however, over an extremely short period of time, but then after the collision, then you'll see the dots still evenly spaced, but they'll be closer together because the constant velocity V final is less than the constant velocity of V1 naught. So then therefore, very noticeably, the tape will change and it will look like this. So right here is then therefore where the collision occurs. If you look at one of the photographs carefully that I've posted for you, you'll see that I wrote exactly where on the tape where the collision occurred. And then this section of the tape corresponds to the V1 naught. This section of the tape corresponds to the V final. For each section of the tape, you'll see me in the other photographs do the following. For example, after the collision occurs, I pick a dot as the origin, and then I number out the following. 1, 2, 3, 4, and so on, out to dot 9. And then I do the same thing counting backwards from before the collision. Counting backwards, I start with a 9 and go 8, 7, and so on, back to a dot 0. So then therefore, I'm going to have these two sections of the tape where I have 10 dots per section. And then for each section, you do the following. Once again, this section corresponds to V1 naught. This section corresponds to V final. Okay, so for each section, you construct the following simple data table. It's going to have just 3 columns. You're going to have, first of all, dot number, which is always referred to as N, 0, 1, 2, 3, and so on, up to dot 9. And then we're going to have the position of the nth dot. The position of the nth dot is going to be measured in this experiment in terms of centimeters, whereas, as is always the case, dot 0 is our origin. So then therefore, using the ruler in the photographs that I've posted for you, you then do the following. For each section of the tape, you measure from 0 to 1, 0 to 2, 0 to 3, 0 to 4, and so on, all the way up to dot 9, and you tabulate that here. And then the last column is the time at the nth dot, where we start the clock at dot 0. Recall that the spark timer makes 60 dots per second, so then therefore the time at the first dot is 1/60th of a second, 2/60ths of a second, and so on. Notice that there is no last column for a velocity calculation. And the reason for that is because we can't use the formula to find velocity that we have used in previous laboratory experiments involving the spark timers, because in this case there are no accelerations. So then therefore, how do you find the velocities, V1 naught and V final? You plot the following. You're going to plot here 2 graphs, one for each section of the tape. Okay, you plot the position in terms of centimeters as a function of the time in terms of seconds. What is this? 0, 1/60th of a second, 2/60ths of a second, and so on. And then because the velocity is constant, when you plot position as a function of time, the dots will form a line. It will be linear, like so. So then what you do is you draw a best fit line. I'm going to go ahead and get a ruler to do that, like so. That's this right here, and then you find the slope, rise over run. Okay, the slope is equal to the velocity in terms of centimeters per second. Once again, you do this first of all for the section of the tape to obtain V1 naught, and then secondly for the section of the tape called V final. So you'll have 2 graphs, 2 slopes of lines, 2 velocities. Okay, and then if we jump back up to the top board, the last thing that we need are the 2 masses. I have measured the masses of these 2 carts for you by using a double pan balance. I post the masses also in a photograph in today's folder. Those masses are in terms of grams. So then what you do is you calculate, there we go, P initial and P final. When you do, it's going to be in terms of grams times centimeters per second as the units, and you just leave it at that. And then we'll compare P initial to P final to each other by calculating a percent error. Here's how I specifically want you to calculate your percent error. Take the absolute value of the difference between P final and P initial, and then we'll make the comparison in the denominator with respect to P initial. So place that there. You'll end up with a decimal, multiply by 100 in order to convert to a percentage. We have obtained a good take for this exercise, so we should get a low percent error. Qualitatively, the major sources of error are an unleveled air track, friction, and you may have noticed that the gold cart V2.0 was not quite equal to 0. It wasn't quite at rest when I did the experiment, but I was doing the experiment by myself. Normally, I would have to have a helper with this experiment, holding on to the gold cart, for example, until just before the collision occurs. Obviously, I couldn't do that in the actual experiment, so I wouldn't be surprised if there is a slight source of error for that reason. Okay, that's how you analyze the data for the one-dimensional perfectly inelastic collision laboratory experiment.